All right, everyone, so this is going to be one of our last types of t-tests that we're going to do, and this is what's known as a matched pairs t-test. And so since this sounds a little bit different in that phrasing matched pairs, we want to know, well, how can you tell when you should conduct a matched pairs t-test? That's our EQ. Well, in some experiments or studies, it does not make sense to have a treatment group and control group. The innate differences between two subjects can be too dramatic and just so numerous to control that we may end up with a lot of confounding variables. So sometimes the best way to compare an individual is to compare them to their own self. This is when we conduct a matched pairs test. Now, a matched pairs test occurs whenever we have each individual compared to themselves. You want to think before and after studies. So for example, if you want to try out a new workout regimen to see if you're going to lose weight, it doesn't really make sense for you to compare your weight to somebody else that completed the program, right? Your biologies are two completely different. So what you'd want to do is measure your weight before you begin your program and then your weight after your program to see if you actually lost some weight. Well, that means it could be effective or not for you, depending on if you lost or gained weight, but what about in general for a whole bunch of people? So that's what a matched pairs t-test can do, is when we have a whole bunch of individuals and we match them up to themselves with before and after. It doesn't always have to be before and after, though. This can also be done with identical twins or two individuals that are very, very, very similar, and then we match up some kind of results. So we might want to compare a placebo to some new kind of drug in identical twins. That way we might be able to try and figure something out there. Now, you're generally going to see two different sets of data, and this is going to be your big indicator that you have a matched pairs t-test, and this helps us understand how to answer our essential question. Okay, you're looking at two different data sets, but each data set is actually going to refer to the same individual. And then what you're going to do is you're going to subtract your corresponding individual results, and you're going to call them the difference. And then you're going to perform your t-test or create a confidence interval and interpret it all exactly the same way that you would have done before. So let's take a look at an example and see how this is done. So here's our example that we have. For their second semester project in AP Statistics, Libby and Catherine decided to investigate which line was faster in the supermarket, the express lane or a regular lane. So there we can see we've got two different kind of treatments in an experiment, right? Now, to collect their data, they randomly selected 15 times during a week, went to the same store and brought the same item. So that way we actually can see we've got some elements of control here. That's good experimental design. One of the students used the express lane and the other used the closest regular lane. To decide which lane each of them would use, they flipped a coin. So there we've got some randomization, and that's good experimental design too. They entered the lanes at the same time, paid with the same method, and recorded the time in seconds it took to complete the transaction. Here's our results. And then we want to carry out a test to see if there's convincing evidence that the express lane is indeed faster on average. So a couple of things that are going to help me out here, right? This key phrasing of the word average tells me I'm looking at t-scores, right? We're looking at means, so we want to make sure we pay attention to that. The other thing that I notice is that we have this, faster. This is indicating a direction. We think the express lane is faster than the average. So let's actually start to go through this. Before we actually write out any of the hardcore stats of it, let's just kind of look at the basics. So the first one, for the first time they bought something, who was faster? 342 seconds in the regular lane versus 337. The express lane obviously was faster. By how much? Well, by 5 seconds. So here's what I can do. I'm going to look at this and define it as the difference, and I'm going to do express minus regular. Defining that order of subtraction is extremely important here, and we'll see why in a little bit. So if I do express minus regular, how much faster was the express lane than the regular lane? It was faster by 5 seconds. Now I have to make sure I include that negative sign because 337 minus 342 is indeed negative 5. Okay? Now how about the next individual, 472. So this is the second time they went. 472 seconds compared to 6 seconds. Well, the express lane was way, way faster. By how much? If I punch this into the calculator to help me out, I get 246 seconds faster. The next time we have, oh, this is a little bit different. 456 seconds in the regular lane versus 502 in the express, showing that the regular lane was actually faster, and they were faster by 46 seconds. So I need to make sure, again, that I include that positive sign. Now, I'll go through and just write out all the subtraction. I've already done this ahead of time. We're just trying to go through this fast, but you get the idea. You're going to subtract each one of these to get the difference. So here we had negative 121 seconds. Express lane was faster. Express lane was faster by 30. Here the express lane was faster by 54. Express lane was faster by 79. This time the regular lane was faster, and that was by 94 seconds. Next, we had, again, the regular lane faster, but only by 17 seconds. Next, we had the express lane faster by 95. Express faster by 20. Express faster by 14. Express faster by quite a bit, almost over 2 minutes, negative 129 seconds. Here we had the regular lane faster by 39. And then finally, the express lane was faster by 42 seconds. So just by kind of glancing at this, which one seems faster? Well, there are a lot more negatives here, right? If there's a lot more negatives, that tends to mean that your first number in subtraction is smaller, which means the express lane is faster, okay? But we don't want to just rely on that, because that's very rudimentary. That's like 8th grade math stuff, right? We are in AP Stats, so let's go ahead and look at the AP Stats way. Let's start off. First thing we can do is we can calculate what is the statistics of all of our differences. So if I call these x diff or x sub d for the differences in all the times, express minus regular, then I can do one variable stats here. If I plug this into my calculator, again, I'm not going to bore you with that. You guys know how to do it. You've done this before. But if we go in, we put in all of these guys here, the difference, into one column, and we put those in, we can get ourselves a mean. The mean that I found was negative 42.6 seconds faster. Then I can also get a standard deviation. Now, the standard deviation is always going to be positive, and this was actually a very, very large number, 84 seconds. So there was a mean difference of negative 42.6 seconds. And what that tells me is that on average, in our sample, the express lane was faster by 42.6 seconds. Okay, so that's a very telling piece of information. But how large was our sample data here? It's only 15 large in our sample, so that's not a ton, right? So what we want to do now is actually start thinking about doing a t-test to figure this out. So if we're going to do a t-test, we are going to need to think about a hypothesis statement. Okay, well, the null hypothesis is again a statement of no difference or no change. So my null hypothesis would be that the true mean difference in time, so that's mu sub d, is nothing. There's no difference between the regular or the express lane. But what we happen to think is that the express lane is faster. So since we defined it as express minus regular, that meant we should have seen that the mu sub difference really is less than 0. Okay, and again, this is why the order in which we are doing our subtraction here is extremely important. Since we said express minus regular, that tells me which order or which direction the sign is supposed to be here. That's less than. If I did regular minus express, the average wouldn't be negative 42.6, it would be positive 42.6. And then we would be using the greater than sign. So you just have to be very careful about defining everything, and this is always how we have to write this stuff out. Now, the good thing is, we've already defined our notation here. X sub d is the difference express minus regular for the checkout times. That's explicit enough. So mu sub d is defined. We don't need to write out that definition sentence, so that saves us some time. Okay, but now let's go ahead and think about, all right, well, what else do I need? Whenever I'm doing a t-test, I think I remember that I need degrees of freedom, right? So degrees of freedom is just n minus 1. So in this case, that's going to be 14. And then we have also, we need to decide on an alpha. So let's let alpha be 0.05. Okay, that seems reasonable enough. And then that's about it that we need to write down. Next, we just need to check conditions. So conditions to check. Did we have a random sample? Yes, we did. We randomly selected times. For checkout. So that's easy. 10% condition. Well, we can think about how large was our sample. It was 15. All possible checkout times. That's our population. So 15 is less than 10% of all checkout times. And again, this is something you can totally write these out in sentences. There's no problem with that. I usually like to use notation because it's faster. Okay, so 15 is less than 10% of all checkout time, so our 10% condition is satisfied. And then we have to check our CLT. Okay, CLT would say that, hey, do we have a sample size that's greater than 30? Okay, we can use the t-distribution. In this case, we don't. Our sample is less than 30, so that doesn't work. Do we know that the population distribution of times is approximately normal? We don't know that our population is normal, so we can't work with that, unfortunately. So then we're out, and we think, uh-oh, do I not have any conditions? Well, here's what we got to do. We got to look back at this guy right here, all of these times, and we have to plot it. Just make a dot plot. It's not that big of a deal. It's a little bit time consuming. I get it. It's frustrating, but hey, you're doing the big boy and big girl stuff here. So let's make sure we are getting there. I like to start off by looking at what were my largest and smallest, or my largest two, or my extremes in differences. So 246, and then I had a positive 94 for when I'm going to make my dot plot. That's how far I'm going to want to stretch this thing out. Okay, so I'm going to extend down here, and I'm going to go and make a dot plot. And I'll have negative 250 to account for that negative 246. And then I'll go all the way up to positive 100. And we'll just go, let's go and mark off by 50s. Negative 200, negative 150, negative 100, negative 50, 0, 50. And I need to extend out a little bit further, 100. And I'm just going to go ahead and plot these down real quick. You don't have to be perfect. You don't have to be super precise. All you got to do is make sure that you are somewhat close here. Okay, so just go through and make your dot plot. All right, so here's my dot plot marking x sub d, the difference in times, and this is in seconds. So what we can see with this particular condition is that there is no obvious skew. This is symmetrical. You might be thinking, oh yeah, this guy might be considered an outlier, but I'm not going to worry too much about that. Skewness is the biggest thing that we want to pay attention to. So we'd say no strong skew, t-distribution is okay. And now we can go ahead and run through with our t-test. All right, so let's go ahead and do that. So when we're carrying out our t-test, I'd like to show you once by hand, and then we'll go through the calculator process. It's really not too tough when you're doing this by hand. You just have to remember the t-score. But if you can remember that it's very similar to a z-score, then it's pretty simple for you to do. So we have x bar minus mu naught. And then we are going to divide that by s sub x over the square root of n. X bar, that's our x bar sub d. Okay, and x bar sub d, we found that from our one variable stats, that was negative 42.6. Mu naught is really mu sub d. What was the mean difference from our null hypothesis? So I'm going to call that mu sub d naught, and that was 0, right? Our null hypothesis said that the difference between these two guys was nothing. Then we divide by our standard deviation. So this is s sub x d, right? So that's really the standard deviation from our sample, which was 84. And then we divide it by the square root of our sample size, 15. This is all calculator work. Plug this into the calculator and we get a t-score of negative 1.964. Okay, with the t-score of negative 1.964, that tells me, all right, we're at least on the correct side of our normal curve, or approximately normal curve, because we know that the mean is going to be 0 after we standardize, and then negative 1.96 is going to be somewhere over here. So this is our t-score, and what we want to see is what is this space right in here, because this guy right here is going to be our p-value. Remember, we want that to be a very small area. So what is that p-value at negative 1.964? Well, at this point, we need to look at the t-table. So if we look at the t-table, zoom in a little bit for you guys to be able to see this more carefully. Remember, what we need to do here is we need to look at our degrees of freedom. So that was 14. And then we need to see in this row, which one is going to, where is our t-score going to go in between? And I see that it's in between these two numbers right here. 1.964 will fall between 1.761 and 2.145. And then we see, well, where exactly is that going to land? Our p-value is going to be in between these two numbers, 0.05 and 0.025. So if I go through and write this out back in my notes here, then we can say that our p-value was going to be in between 0.025 on the left end. So p-value is going to be bigger than 0.025, but it's going to be less than 0.05. And this is really all we care about. The fact that p-value is less than 0.05, because what was our alpha? Our alpha, we remember from up the top, was 0.05. So sure enough, our p-value is less than alpha. So when our p-value is less than alpha, what do? So we reject the null hypothesis. I have convincing evidence that the express lane is indeed faster. On average. All right, there you go, you guys. That is doing a t-test, and that's doing it by hand, and that's really not that tough, right? Most of the legwork is done in the beginning with any of these tests. Now, if you want to use your calculator, that's perfectly fine. We can run through that and see how that works. Going through our calculator, we'll bring up a calculator page here. We go into our menu. Oops. Go and hit enter for a calculator page. Go into our menu. We're going to choose number 6, statistics, and then we want to choose number 7, stat tests. And then with our stat tests, remember that we are going to choose a t-test. This is option number 2. Our data input method here, since I've already developed the stats, I can go ahead and use that. So I'll go ahead and hit OK. And then our mu naught, remember this is what was from our null hypothesis. We said the difference between the two means was 0. And then the x bar that we had, again, the signs are very important here. We had negative 42.6, and then we had a standard deviation of 84.0, so all I have to do is hit 84 here. Our sample size was 15, and then we have to double check our alternate hypothesis. It indeed was not this guy here. It wasn't a two-sided test. It was just a one-sided test. We said that the mean was going to be less than 0. And we get our results, and we can sure enough see, hey, our t-score was right, negative 1.964, and look at our p-value, 0.348. So that gives you a more precise p-value, but 0.0348 is still less than 0.05 alpha, so it's all correct. So either way you do this, it doesn't really matter. You can do it this way if you want, or you can do from t-test, your p-value was equal to 0.03845, and sure enough, again, that is less than alpha. So that's it. That's doing a match pairs t-test. Not really all that different. You just have this couple of steps in the beginning that you have to take care of. That's it, guys. Thanks for watching. Have a great day.